we continue the chapter work, energy and power. And in the last video, we were discussed about perfectly inelastic collision. And about perfectly inelastic collision, if two bodies stick together after collision, if after collision two bodies stick together and move as a single body. Two bodies stick together and move as a single body with common velocity. After collision, if two bodies stick together and move as a single body with a common velocity, then such type of collision is called perfectly inelastic collision. And in perfectly inelastic collision, momentum is conserved, but the loss in kinetic energy is maximum. Loss in kinetic energy is maximum and momentum is conserved. An example, mud thrown on a wall and sticking to it. The second example, bullet fired into a wooden block. Now the next type of collision which we discuss is super elastic or explosive collision. Super elastic or explosive collision. Super elastic collision or explosive collision. So in super elastic collision, there is an increase in kinetic energy. In such a collision, there is increase in kinetic energy. There is increase in kinetic energy. In superelastic collision, there is increase in kinetic energy. And examples are bursting of a cracker when it hits the floor. Examples are bursting of a cracker when it hits the floor. Forcefully. So the example of superelastic collision is bursting of a cracker when it hits the floor forcefully. Then we discuss about head-on or one-dimensional collision. Head-on collision or one-dimensional collision. Head-on or one-dimensional collision. This is another type, head-on collision or one-dimensional collision. So in this collision, the colliding bodies move along the same straight path. It is the collision. It is the collision in which it is the collision in which the colliding bodies move along the same straight line. In which the colliding bodies moves along the same straight path. It is the collision in which the colliding bodies moves along the same straight path. It is the collision in which the colliding bodies move along the same straight path before and after the collision. Before and after the collision. Suppose there is a body A of mass m1 moving with a velocity u1, and there is another body of mass m2 moving in the same direction, and after collision they are again moving in the same direction with their different velocities. So the colliding bodies moves along the same path. The colliding bodies moves along the same path before and after collision. Then such type of collision is called one-dimensional collision or head-on collision. An example is collision between two railway compartments. Collision between two railway compartments. Collision between two railway compartments is an example of head-on or one-dimensional collision. So in one-dimensional collision, if the colliding bodies move along the same straight path before the collision and after the collision, then such type of collision are called head-on collision or one-dimensional collision. And examples are collision between two railway compartments. Next we discuss oblique or two-dimensional collision. Oblique or two-dimensional collision. Oblique collision or two-dimensional collision. If two bodies do not move along the same straight path, if two bodies do not move along the same straight path, if two bodies do not move along the same straight line path, if two bodies do not move along the same straight line path, but they lie in the same place. If two bodies do not move along the same straight path, but they lie in the same plane, before and after collision. But they lie in the same plane before and after collision. Then such type of collision is called oblique or two-dimensional collision. Such type of collision is called oblique or two-dimensional collision. So if two bodies do not move, along the same straight line path, but they lie in the same place, before and after collision. They do not move in the same straight line path, but they must lie in the same plane before and after collision. Then such type of collision is called oblique collision or two-dimensional collision. Examples: collision between two carom points. Collision between two carom points is an example of oblique collision or two-dimensional collision. Because after collision and before collision, they are not in a straight line path, but they lie in the same plane. So such type of collision are called oblique collision or two-dimensional collision. Now the next topic is the conservation of linear momentum in a collision. Conservation of linear momentum in a collision. Conservation of linear momentum in a collision. Suppose there are two bodies. Suppose there are two bodies, 1 and 2. Suppose there are two bodies, 1 and 2, collide against each other. We suppose that there are two bodies, body 1 and body 2, and they collide against each other. They exert mutual impulsive forces. They exert mutual impulsive forces on each other. They exert mutual impulsive forces on each other. They exert mutual impulsive forces on each other during the collision. So we have supposed that there are two bodies, body 1 and body 2, and they collide against each other, and during the collision they exert mutual impulsive forces on each other. During the collision time, delta t, in a very small interval of time, for a very small, the collision exists for a very small interval of time. Delta t is the small interval of time. Collision duration, delta t. There are two bodies, 1 and 2, which collide against each other, and during the collision in time delta t, they exert impulsive forces on each other. And we know that change in linear momentum for body 1, delta p1. Change in linear momentum for body 1, delta p1 equals to F12 into delta t. Change in linear momentum is equals to impulse. Impulse equals to force into time. Force acting for a very small interval of time. So change in linear momentum of the body 1 must be equals to impulsive force for time delta t. Similarly, change in linear momentum in body 2, P2 equals to F21 into delta t. These are the change in linear momentum in body 1 and body 2, where F12 is the force exerted on body 1 due to body 2. F12 is the force exerted on body 1 due to body 2, and F21 is the force on body 2 by body 1. Force exerted on body 2 by body 1, and F12 force on body 1 due to or by body 2. But these two forces must be equal and opposite. From Newton's third law, F12 is equals to minus of F21. These two forces which are acting on each other, F12 and F21, must be equal in magnitude, but they are opposite in direction. So multiply both sides by delta t. So F12 into delta T is equals to minus F21 into delta T. And F12 delta T is written as delta P1 equals to, and F21 into delta T is written as minus delta P2, and delta P1 plus delta P2 equals to 0. And taking delta as common, we get P1 plus P2 equals to 0. It means P1 plus P2 equals to 0. And 0 is constant term. Therefore, the sum of linear momentum of two bodies remains conserved. The value of P1 plus P2 is constant, and this is the conservation of linear momentum in a collision. So we have supposed that there are two bodies, 1 and 2, and they collide against each other, and during the collision they exert mutual impulsive force on each other. F12 is the force acting on body 1 due to the body 2. F21 is the force on body 2 due to body 1. And delta P1 change in linear momentum equals to impulsive force F12 into delta 2. Similarly, delta P2 equals to F21 into delta T. And these two forces are equal in magnitude, but they are opposite in direction. Multiplied both sides by delta T. So F12 delta T equals to minus F21 delta T. This is written as delta P1 and this is minus delta P2. And taking delta as common, we get P1 plus P2 equals to 0, which is a constant term.